This is the Calculus BC end of year project exploration, and I wanted to spend this year looking at Fourier series. So I started the class with a launching point of exploring legendary 8-bit music. So through navigating the web, I found this brilliant designer here who created something like this. And you'll see here, elegantly mapped out, is the 4 tracks available on the NES system, where 2 of the tracks receive only square waves, while 1 track only triangle waves, the 4th track a noise track, and then there's actually a 5th channel down here that was rarely used from what I found in my research. And he kind of does a little of all the famous songs, but you can see still square waves, triangle waves, and then square, square. So, I think it got the kids excited and gave some relevance to the onslaught of Wolo lectures they had to then listen to. And you can kind of see here where the direction of the lectures took. Started out with the goal of creating a square wave of amplitude 3 here, and a specific example of a 2 pi wavelength, and the idea of converting any function into a vertical shift plus a certain intensity per each harmonic frequency. So all of these coefficients would have to therefore be solved. And the idea being, the larger the coefficient related to that particular harmonic means that this is a more prevalent wave inside of this wave. So that's the idea. We have to figure out how to solve for the intensity of each frequency. And we fast forward over to the south board here. This is a 3-board problem. It's about a 60-minute lecture series here. And here we see these are the 5 properties that we need to prove. And the first 2 are pretty immediate and direct. I mean, a little short proof here. Same goes for the second line. But the 3rd, 4th, and 5th identity take a little more work. We got to use a addition of sine formula. So we want what is a sine A cosine B. We know that the sine of A plus B is here. The sine of A minus B is here. Using a linear combination, we can solve for sine of A plus B is the sine of A plus B plus the sine of A minus B divided by 2. So using that substitution, it's actually a fairly straightforward proof. We make the substitution here, which allows the elimination of the product. And the product is what causes the integration problem to be more challenging. So we remove the product, and we've already shown that sine of any integer, regardless of whether it's 0 or not, has an area of 0. And then we have to go and do the similar thing for the other 2 identities. But you can see here, well, if we want sine, then we have to use the cosine A plus B, because that gets us our sine A sine B. So once again, in another system of equations, we can simplify sine into a removal of the product, giving us a simpler cosine function only. And we already shown that the integral of a non-zero frequency for cosine is 0. So it makes a very simple problem, gives us pi. And fast forwarding through, that was a 60-minute lecture in about 2. So bear with me and feel free to pause it if you want to see what the board says in slower time. Here we end up using that identity that the coefficient of an must be 1 over pi times the cosine nt times the function, and bn is the sine. So after doing this for this specific wave, we see that the function value is either 3 or 0 on the given intervals, which simplifies later to 0. So in other words, every coefficient of every harmonic frequency involving cosine is 0. So all of these are 0. There are 0 cosine curves with the fundamental frequency 1. There are 0 cosine curves with the twice the fundamental frequency. And then similarly, we use the Bn to find the intensity of each sine curve. We know that the function is either 3 or 0, but we ignore the 0 because that's 0. And then when we do the integral problem, you end up getting this interesting case of, well, cosine pi n is either an alternating -1 or 1, and therefore we only care about when n is odd, because when n is even, this becomes 0. So we get the 6 over pi n formula, which helps us because now we know only n odds, or only odd n's, produce an intensity with that particular frequency. So here we'll see that the B1, the fundamental, has an intensity of 6 over pi times 1, while B2 is an even frequency, so then we don't need that one. So we then go to B3, which that's 3 times the fundamental, which means that's going to be inside of our curve with the intensity solved by 6 over pi n, 6 over pi 3. Then we fast forward to the 5th fundamental, etc., or the 5th harmonic, sorry, of the fundamental. And we see that there's an easy pattern of it's always 6 over the odd values times pi, and then 6 times the odd scalars of the fundamental, and I'm using the fundamental of the 1 here, which in a second we're going to use the fundamental of 40, and we'll talk about why in a little bit. So you can see, fast forward through, we've created the successful series, a Fourier series, for the square wave. Very exciting. Even though it was a 60-minute lecture, I felt that the kids were entertained because of the launch. Right? The launch is always what's going to leverage that time and attention span. So moving forward, well, our job is trying to make music here. So we steal this reference chart where 440 hertz is indeed the A. And that's the middle A, the A4, which is, as you can see here, usually the tuning reference. That's why we're picking it. And I found this software called JSID app. And what the JSID app does is allows you to plug in a frequency. So you kind of do this drag, and then you can connect your frequency to the synthesizer here. And we're only doing a pure tone in there. So you can see that I've selected a curve, gave it the frequency of 440, so this should be producing the sound of A. And then when we finally throw it into our synthesizer and synthesize, you can see that this is just a standard sine curve. And when we play it, that's the noise that it produces. So that's a pure tone. Now, luckily, there are actually options here where we could have just picked the square wave and synthesized and gone from here to here. And then, we could have just played that directly. But then the whole purpose of teaching the Fourier series would be irrelevant because we're just letting technology do all the work. We're trying to teach programmers to design the next technology, not people who are using the current technology. So I think that's an important side note, that we need to teach the underlying math so that we're creating the engineers of tomorrow. So we stick back to this sine. And the interesting part is, here you'll see that this is the creation of a pseudo square wave. It's not a pure square wave because I'm only using a finite number of curves here. To get the pure square wave, I would need many, many more to be even closer approximation, or infinity to be a pure square wave. So how do we go about building it? Well, we already kind of constructed that once I pick the fundamental, the only waves inside of my square wave are the odd scalars of that fundamental frequency. So you'll see that this is 1 3, 5, 7, 9, 11, and 13 for my scaling product of the fundamental. And the amplitude, if I went back, you would see that the intensity of each frequency is inversely proportional to the scalar that I'm choosing. So when I chose my first frequency, this was 6 over pi times 1. But when I chose the next one, that should be 6 over pi times 3 and 6 over pi times 5, etc. Now keep in mind this is an approximation for that value in a calculator because I don't think pi was an accessible format here. So after doing this and synthesizing all of these waves together, right, we end up seeing that this is an approximate square wave. And the cool idea is here we get to see the square wave noise, or what that we're assuming is the A440, and we compared it to the pure tone of A440, and I don't know if that's even detectable in this. There it goes. And here, so the cool thing is they're both A440s, but they do have a different timbre. Right? And that timbre is kind of the next stage of our exploration of how to pick out these frequencies that are sort of in the background that we don't hear necessarily, but it does affect the sound quality of, like, and that's going to make the difference between an A440 on a piano, an A440 on a synthesizer, an A440 on a violin. All of those frequencies of lower, all those sine waves of much higher frequencies that have much less intensity. So we're not detecting them as much, but they're there underlying in the sound, changing the quality and timbre. So that's sort of our next exploration part. Hope you enjoyed. I'll try to make some more videos and updates about how this project and Explore is going. Thank you.